In this episode, we're welcome. This is not an episode, but an episode of sorts. So in this video, we're going to continue our exploration. So this is going to be part 9 of our exploration of Lagrange's theorem. So this is part 9. Well, so we proved Lagrange's theorem successfully that if G is finite and H is a subgroup of G, then the order of H must divide the order of G. Okay, we established this. Now the question, well, what is Lagrange's theorem good for, right? What are the consequences? What are the consequences of Lagrange? Right? What are the consequences of Lagrange's theorem? So far, well, we looked at a couple. So for instance, we realized that, look, if we actually have a group G, okay, we have a group G that's finite, and we pick some element little g of big G, then it actually turns out that the order of G divides the order of big G. And we managed to prove this using Lagrange's theorem. Alright, let's look at another consequence. Well, let's actually determine if it is a consequence or not. Suppose suppose that the order of G equals to some prime, right? P is prime. What can we say about the group G? Right? What does this imply about the group G? Right. So firstly, if so we repeat that. Suppose we found that the order of a group is actually P, some prime P. What does that tell us about the order of the group G? Okay. For instance, how can we write the elements of G? Are we allowed to write the elements of G as 1, G1, G2, all the way up till G to the sub P minus 1? How many elements do we have here? Well, do we have P elements? How many elements in the group? P of them. So, are we allowed to write the group like this? Just G1 is some element, G2, and etc. Okay. Well, now let's ask the question. Suppose we got G sub I, element of G. Okay. And we're going to suppose that G sub I is not equal to G. Sorry, G sub I is not equal to the identity. So we're picking some non-identity element in the group. Well, what are the possible orders of G sub I? What are the possible orders of G sub I? Right. Well, what does Lagrange's theorem tell us? Right. Lagrange's theorem tells us that, well, do we even want to go this route? Sure, why not? Why not? Okay. So, we proved before that Lagrange's theorem tells us that the order of G sub I must divide, the order of every element of the group must divide the order of the group. So the order of G sub I must divide the order of G. Given that the order of G sub I must divide the order of G, we ask the question again, what are the possible orders of G sub I? Can G sub I equal to 1? Okay. Does 1 divide order of G? How about P? Suppose the order of G sub I was P. Does P divide the order of G? Right. Natural question, is there anything else? Is there anything else that the order of G sub I can be, given that the order of the group is P, some prime P, and the order of G sub I must divide the order of the group, which is a prime. Right. So are we saying then that the only possible orders of G sub I are 1 and P? Alright. If the possible orders of G sub I are 1 and P, alright, can the order of G sub I, how do we eliminate these options? How do we determine, because the order of G sub I can't be two things, so the question, what is order of G sub I? We've said order of G sub I can either be 1 or P. But what is the order of G sub I actually? What is it, is the question. How could we determine? Does it mean that perhaps we have to show which one is not? Do we need to maybe do some elimination? Let's think about it. Suppose the order of G sub I equals to 1. What would that mean? Would that mean that 1, G sub I raised to the 1 equals to 1? But if G sub I to the power of 1 gives us the identity, doesn't that imply that G sub I is itself the identity? But how can G sub I be the identity if we suppose that G sub I is not the identity? Right? So are we saying that assuming that the order of G sub I is the identity leads to a contradiction? If the order of G sub I being equal to 1 leads to a contradiction, what can we conclude? Can we conclude that the order of G sub I is not 1? If the order of G sub I is not 1, what has to be the order of G sub I? Right. So can we conclude then that, okay, let's get a better color here. Let's put it like that. Yeah, let's get a better color. So, oh geez. All right, there we go. So let's just get the dark color back. So can we conclude then that, are we saying that the order of G sub I has to be a prime, has to be the prime P? All right. So now, if we had our group here G, which had the elements 1, G1, G2 to G sub P minus 1, and we pick some element G sub I in the group G and found that the order of G sub I equals to P. Okay. But what does that mean? What does that tell us about the group G? So let's examine a certain subset. Let's examine the subset. Okay, let's create some space here. Let's examine the subset G sub I to the 0, G sub I to the 1, G sub I to the 2, all the way till G sub I to the P minus 1. Okay. First question. Is every element of this set an element of G? Let's call this subgroup H. Just let's call this, we don't know it's a subgroup yet, so let's call it the set H. Well, is every element of this set H gonna give us is every element of this set H also an element of the group G? That is G sub I to the J, right, J is some power of G sub I, is that an element of the group G? What do you think? Isn't G sub I to the J the same as G sub I times G sub I multiplied J times? If G sub I to the J is G sub I times G sub I times G sub I multiplied J times, and G sub I is an element of G, doesn't that mean that G sub I to the J, this product has to be an element of G? Isn't that a consequence of the fact that the group is closed? Right? So if G sub I to the J is actually an element of the group, for any J, can we at least conclude that H is a subset of the group G? Alright? Well, if H is a subset of the group G, right, let's think about the cardinality, the size of H. How many elements are in H exactly, right? So we notice here that, well, does H actually have P elements in it? Right, is a question. Because, I mean, suppose we've already seen that H is a subgroup of G. Suppose we were able to conclude that the order of H equals to the order of G. Okay? What would that imply? Would that mean that G equals to H? That actually the group G can be generated by one element, namely G sub I. And it actually really is G sub I to the 0, G sub I to the 1, G sub I to the 2, all the way till G sub I to the P minus 1, right? Would proving that the cardinality of H equals the cardinality of G lead us to conclude that the group G is actually equal to the group H, right? And in fact, be able to conclude that the group G is generated by one element, namely G sub I. Okay? Well, how can we prove that the order of H equals to the order of G, right? So, can we conclude that already? What's the order of G, right? Didn't we say that the order of G was P? How many elements are in H? 0, 1, 2, up to P minus 1. Does that mean we have P elements of the group H has elements P? Sorry, the set H has elements P? Sorry, does this mean that the set H has P elements in it? Well, what if, let's say, some two of the elements in H are actually the same? What if maybe G sub I to the 1 equals to G sub I to the 2? Would it then be possible for the group H, for the set H to have exactly P elements? Wouldn't the set have less elements if some of the elements are the same? So what would we need to show in order to prove that the order of H is actually equal to P, which is actually equal to the order of G? Right. Would we need to show that for some for some for some jk, g to the I integers, of course, g to the I j does not equal to g to the ik, right? Suppose we're able to prove this, that g to the ij does not equal to g to the ik. That is that no two elements in H are the same. None of these elements are the same. Would we be able to conclude that the cardinality of H equals to P? Right? So let's look at G sub I to the J. Suppose that G sub I to the J was actually equal to G sub I to the K. Alright? What would that mean? Well, I mean, without loss of generality, we're assuming J does not equal to K, by the way. So we're assuming J does not equal to K, and in particular let's assume that J is less than K, right? Suppose we assume that J is less than K. What would saying that G sub I to the J equal to G sub I to the K mean? Right? Because G sub I is an element of the group G, doesn't it mean that there exists some G sub I to the J inverse? Right. Okay. So what does that tell us about our equation here? Suppose we multiply both sides by G sub I to the J inverse. What equation would we end up with? Would we end up with G sub I to the J inverse times G sub I to the J equals to G sub I to the K? Alright, so we just run out of time. Please try to see if you can prove that the order of H actually equals to the order of G, right? And here H is being taken to be G to the 0, G sub I to the 0, G sub I to the 1, all the way up to G sub I to the P minus 1, okay? Is this enough to, can we conclude that order of H equals to G? And if order of H equals to G, what does that tell us about the group G? In particular, does it tell us that G can actually be generated by the element G sub I? Can G be generated by the element G sub I? Right, is the question. All right. And if so, what does Lagrange's theorem tell us about if we have a group which has prime order? What can we conclude? Right. So please think about that, and in the next video we'll be able to explore further this idea. Thank you very much for watching this video, and have a relentless week. Bye.